Cool. So welcome back, and why don't we just get started? So before I start, let me just kind of recap very briefly what we went through last time and tell you where we're going in this lecture and then my next lecture. We kind of worked through the actual, practical elements of the bootstrap in general dimensions, working through the case of gauge theory and gravity. And hopefully you saw that the, kind of usual textbook formulations of things, like gauge theory and gravity, Yang-Mills theory, those structures are not, simply brilliantly constructed. They're actually mandated by very simple principles. Okay, so actually let me share my screen so I can actually show you some of these bullets here. Okay, so hopefully you should see my broadcast. Okay, cool. Cool. So hopefully I think you can see this. Just let me know if you can't. Anyway, last time, just to recap, we showed that very elemental principles, which include Lorentz invariance and factorization, really solely, was enough to dictate extremely rigid properties of the interactions. Okay, so we're used to kind of thinking that if we talk about gauge theory, then we think of it maybe as an example of a massless spin 1 particle with that interacts non-trivially. But the kind of point of the last lecture was to show that this is actually directionally implying the other way, which is that the only, or I should say the unique theory of massless spin 1 that interacts with the number of derivatives that we assumed, which was one derivative in the elemental 3-point function, that actually dictates the structure of gauge theory. Okay, we fixed the 3-point function that way, and then 4-point we built from factorization. And the kind of crucial fact was that all of that, all of that kind of backstory of the Lie algebra and Jacobi identities really just came as consistency. Okay, so the point here is that massless spin 1 is implying this. The same logic goes for massless spin 2 and gravity. Okay. Now, of course, we could kind of widen our assumptions by allowing for more derivatives than we initially assumed, and you can get higher derivative corrections of both. So there's no inconsistency, no statement of complete uniqueness. Effective field theory similarly basically drops into our lap by building functions with the right properties, and we learn that all the higher dimension operators in gravity and gauge theory are really just other types of amplitude structures that we can write down. And that's a very powerful just statement right there. Okay, basically this is us relearning that gauge symmetry is not actually a symmetry, it's just simply Lorentz invariance and factorization together. Okay, now what I have not told you anything about is really the scalar case. Okay, for the massless, even the massless scalar case, it was largely unconstrained. Okay, that was kind of probably clear from what I did, which is that maybe some amplitudes had vanished by Bose symmetry, but for the most part, this was very much unconstrained. Now, this is, if you like, a problem if you want to reproduce as much of QFT as you can, because of course we know that while there are gauge symmetries and diff symmetries that are not really physical but are redundancies of description, there are legitimate symmetries, global symmetries, which act, for instance, on scalars. Okay, so classic example, just even in the standard model, of course, there's many kind of approximate accidental symmetries, but there's the chiral symmetry, which is a classic example, which is non-linearly realized in the so-called chiral Lagrangian, which describes pions at low energy, in the low energy strong interactions. Okay. Now, what this talk is going to be about is basically understanding how to bootstrap this class of theories, scalars. Okay, and I'm going to call this the soft bootstrap for reasons that will become clear. But what's going to be interesting is that we're going to learn that lots of new theories beyond gravity and gauge theory appear. Okay, so we're going to be talking about pions. So lots of spin 0 particles. We're talking about pions. We're going to be talking about particles that show up in modified gravity and beyond the standard model cosmology, which include DBI, Born-Infeld type fields. We'll be talking about Galileons, all kinds of kind of more exotic things, which aren't being just randomly inserted here, but will actually arise naturally from the constraints of this bootstrap. Okay, so that's the first thing I'll talk about. Hopefully, I might go through this even a little quickly, this lecture 3, so I can get to actually the next set of slides, which will be about all the structures that are very non-trivial that relate gravity, gauge theory, and pions, Galileons, and this whole kind of gambit of theories. Okay, so this is kind of this first lecture 3 is going to be my path to actually deriving some of these scalar theories, but then we're going to see how they're all connected to gravity in some very interesting way, which is in some sense where the real fun begins, because it's not just rederiving facts we know. Okay, so this is really the question: how are scalar EFTs constrained, or really scalars in general? Okay, this is of course the classic Mexican hat or a wine bottle potential, where you put something here, it tachyon rolls the field off, and then you have a Goldstone boson at the bottom. Now, to describe this with QFT, we have of course a beautiful, quantum field theory is perfect for this. Effective field theory is designed for this. But if we do not have fields because we're studying amplitudes, then what could it possibly mean to describe a symmetry of them? Okay, right? If I have discarded fields, then how can I talk about symmetries that are global? Okay, it seems like that's missing from this amplitude story, and I want to tell you how it's actually not missing. We can re-include it by inputting symmetry in the language of amplitudes, essentially. Okay, so we're going to talk about these kinds of EFTs, essentially Goldstone bosons of different types. Okay, now here's the kind of toy version of what I want to say. So of course, if we have a non-linearly realized symmetry, like phi goes to phi plus constant, the classic story that you say is that this is a U1 Goldstone boson. It has a shift symmetry. You write down a Lagrangian that exhibits that shift symmetry, which means it's only a function of derivatives of phi. Okay, where this Cn is some arbitrary coefficient. Okay, just given this symmetry, it does not fix the coefficient Cn. So you just write down an effective Lagrangian. And then maybe as an afterthought, you might compute amplitudes. And as is pretty obvious, you know that if you compute a scattering amplitude in this theory, and you take a single momentum p, right? So that's for any leg, and you send it to be soft. That is to say, you take its energy and momentum to be 0 in a uniform way, maintaining on-shell conditions. Then what you find is it actually vanishes with p, okay? So as p goes to 0, the amplitude will be 0, and it will go to 0 linearly with p. Okay, so these are called soft zeros. This is like the toy version of what's called the so-called, maybe called Adler zero in the case of the chiral Lagrangian. Okay, but the usual implication is we start with the symmetry, we build a Lagrangian, then we start with this, and then we build amplitudes, and we learn an interesting phenomenological fact. Now, as is usual in amplitudes, I want to go the exact reverse direction. I want to input the soft zeros as a physical constraint. Okay, so I'm going to basically bootstrap an amplitude with soft zeros as an input, and then derive this action. Okay, now as you might imagine, this very simple case of just the amplitude vanishes with 1 power p is very simple. It's not that impressive to get this Lagrangian from that, but what we're going to find is something kind of much more interesting, which is that by taking this bootstrap to its kind of logical conclusion, we can not just derive this simple action, but we can actually learn about a whole set of, in some cases, hidden symmetries, but in some cases, completely new symmetries using amplitudes. And I'll describe one such instance in this talk. And by new symmetries, I don't mean a symmetry understood a new way. I mean a symmetry that had never been seen or understood with Lagrangians until this type of analysis was done. Okay, so in other words, a new symmetry in theory was actually understood by this analysis, and I'll highlight that when that shows up. Okay, but the idea is to reverse the bootstrap and to try to learn about symmetries. Basically, go two steps up to determine what kinds of symmetries are implied by amplitudes principles that you can impose simply on these kinematic functions. Okay, so let's push forward. Okay, so before I kind of do this systematically, I want to give the right kind of language to describe the space of all scalar field theories. Okay, right. The idea here is to really understand massless scalars in their full glory, which means I need a way of classifying scalar theories that will be useful for our kind of amplitudes analysis. Okay, so that's why I'm going to call this the classification of theories, of scalar theories, basically hinging on their number of derivatives. Okay, but it's going to be, if you like, a way of kind of stratifying theories based on number of derivatives they have in their interactions, but one that's very well tailored to amplitudes. Okay, so we're going to try to write down a general parameterization of a derivatively coupled EFT of scalars. Okay, now I want to kind of emphasize here that we can in principle allow for general flavor structures, so like more than one scalar, and also I'm being very schematic here with the partial derivatives, right? So there's let me just say what I mean here. I'm just saying that there's two derivatives and two phi's at least, and then I'm defining every other operator as the remaining derivatives acting on some number of other phi's. Okay, this is of course schematic because I can have many different contractions of Lorentz indices, amongst these lambdas, but also maybe even amongst these. Okay, I'm being very schematic about which mu and nu's are contracted. This is really just a classification based on counting numbers of derivatives. So it doesn't even really matter who the derivative is acting on, if you like. The idea is I'm factoring out two derivatives here, two phi's here, and then I'm stratifying all the interactions in terms of this lambda mn, which parameterizes those couplings. Okay. It may seem puzzling why I factored out this piece, but hopefully it will become clear in a second. Okay, so the idea now is to write basically every scalar field theory that you know of in this language. And we want to ask about hidden symmetries or nonlinear symmetries that such a theory could exhibit without actually building the symmetry or the Lagrange. Okay. Now, I want to consider a subclass of nonlinear symmetries which satisfies a certain condition, which I think is quite general, although you can certainly relax this assumption, which is that I want to imagine there's some generators of this nonlinear symmetry, and I want to imagine that the symmetry commutes with dilations. Okay, so this is just my fancy way of saying that I could rescale all the momenta in this theory of massless particles, and that rescaling will commute with all the nonlinear symmetry generators of this. Okay, so in some sense, I'm kind of disentangling T from intrinsic four-dimensional or space-time isometries. Okay, so T is in some sense internal. That's at least a sufficient condition for this to be true. Now, why do I want this to be true? Okay, so I wanted this to be true for the following reason. If you have a non-linearly realized symmetry at a Lagrangian level that relates operators at different numbers of fields. So for phi to the 6th and phi to the 20th are connected by non-linearly realized symmetries. From the point of amplitudes, of course, we don't have fields. What we have is something a little more interesting, which is interference between terms in the amplitudes. Okay, so the idea is the following. Look at an amplitude and find terms that scale as some overall power of momentum. Okay, so just count the number of powers of momenta in a given term. Let's say it's p to the 6th. You find all such terms. Okay, some could have poles, some could not have poles. The point is that all of those should interfere in some complicated way for there to be nonlinear realized symmetry. Okay, so this is me just saying that the kind of relations between fields, so operators in the Lagrangian of different numbers of fields, this enters into amplitudes as basically destructive interference between terms. Okay, let me be very concrete about what I mean by that. Okay, so let's imagine we just computed even with Feynman rules. So this is some endpoint function, and there's like a contact Feynman diagram, and then there's a factorization Feynman diagram. Okay, so I'm not even using amplitudes to do this, but of course you could do a bootstrap and build these objects. But let's say I just use Feynman rules using this Lagrangian. Okay, now this first piece has a momentum to the m plus 2 by definition. This vertex here has this factor, which is m prime plus 2. This one has m double prime plus 2, and then there's the propagator in between. Okay. Now the point I was making before was that let's say I want this diagram and this diagram to destructively interfere. That is to say, for them to cancel with each other. Okay. That means I need the total number of powers of p here to be the same as the total number of powers of p here. So these powers of p need to be the same. And a sufficient condition for that is this. Okay, so it gives, in other words, I'm writing down a slew of operators with different numbers of derivatives. But if this relation is true, then this contact term and this factorization term have the same, if you like, homogeneity scaling with p, the same overall power of p. And another way of saying that is I could define some fixed parameter rho, which is given by m over n. Okay, and I'm going to call this a power counting parameter. Okay, so in other words, I define a theory such that m over n is always the same number rho for every interaction. Okay, in other words, there's a whole set of terms here that sum over m and n, but I only sum over m and n such that the ratio is some number rho. Okay, so let me be concrete so it's a little bit clearer. Okay, so again, just counting derivatives, we have a d phi squared that I factored out in front. And the statement is of this definition of rho is just that the rest of the interactions have rho derivatives per field. Okay, and this f is some nonlinear function, but the point here is that rho is kind of counting the number of derivatives per field modulo this prefactor. Okay, now one thing I want to say is that this classification applies actually very generally, and you can include higher spin in this story. Okay, so I've kind of angled this to be scalars, but you can actually replace these with spin 1 and spin 2 particles. If you like, completely fine, as long as, of course, that you write down sensible theories. And you can count the number of derivatives and do the same analysis. And for this reason, basically every theory you've ever heard of or any theory you've ever seen that has a name is classified by this rho parameter. Okay. Here, rho equals to 0. Let's just go through them. Rho equals to 0 means that this is no derivatives on phi, which means that the Lagrangian looks like d phi squared times a function of phi. Okay, so an example of this was one of the first theories I showed you, which was the vanishing trivial theory. But also, if you add flavor, we know that this is actually precisely the nonlinear sigma model's type of power counting. The nonlinear sigma model has two derivatives, one derivative here, one derivative there. And then when you expand the U field, you get a whole power of pion fields. So the NLSM is of this type. Another example is GR. In GR, the Ricci scalar has two derivatives, and for the same reason as for the NLSM, when you expand the graviton, you get exactly this form. Of course, there's additional indices because it's a spin-2 field, but the point here is that GR and pions, actually, in terms of the dimensionality counting, are actually very similar. There's a very close analogy between them, and that's why neither of them is renormalizable in the kind of classical sense, but you can, of course, renormalize them in power counting, in powers, in the power expansion and higher dimension operators. Okay, so that's rho equals to 0. Rho equals to 1 is another simple case. This is when there's precisely one derivative per field in this function. One example of that is a U1 Goldstone boson, okay, which I just wrote the Lagrangian for up here. Yeah, this guy, U1 Goldstone boson, okay, that has exactly one derivative per field. Another example is the Euler-Heisenberg Lagrangian. So if you integrate out the electron and just look at E and M at low energies, then it's a function of the field strength, and the set of terms which are just a function of the field strength is known as the Euler-Heisenberg Lagrangian, which famously can be computed exactly at one loop by integrating out the electron world line. We can keep going. Okay, so we go to rho equals 2. Rho equals 2 means there's even more derivatives per field. This is a type of theory that's called a Galilean, which shows up in Beyond the Standard Model cosmology. It has nothing to do with violating Lorentz symmetry. It's just kind of an unfortunate name. It comes from an extended shift symmetry of the scalar, which looks like a Galilean symmetry, but it's completely Lorentz invariant. I'm not putting the kind of proper coefficients here, but it's just a very high derivative theory. Okay, and it has a very interesting feature, which is that despite having a higher derivative, it has no ghosts through some cleverness, which is similar to certain other modified gravity theories. It actually has no Ostrogozzi ghost, which is a cute feature that it has. In fact, it was designed for that. Now, rho here I chose to be 0, 1, and 2, but you can pick more exotic values. Okay, so you pick rho equals to -1. That may seem strange because there's a -1 derivative here, but just keep in mind, I'm not actually saying antiderivative or integral. I'm just counting derivatives. Okay, so when I say -1 here, all I mean is that when you expand this and you look at the number of derivatives, there's fewer than 2 derivatives per field in the interactions. Okay, so if you think about Yang-Mills theory, it's precisely of this form. The cubic interaction has 1 derivative. The kinetic term has 2 derivatives. So if you like, it's almost like you put a derivative inverse in the cubic interaction, so it's precisely of this form. Okay, similarly, phi 4 is also of this form, and so on. Okay, so it's really, again, I want to emphasize this is a schematic counting of just derivatives. This D inverse is not like an antiderivative in any formal sense. Okay, rho equals -2 is the last case, and this is just phi cube theory. Okay, so the upshot here is that every theory that you've ever seen that has a name, not surprisingly, the structure they have is fixed by principles. This is, of course, chiral symmetry, diff symmetry, nonlinearized U1, really gauge symmetry, Galilean symmetry. Okay, these all have symmetry principles associated with them. but they're all blocked into certain fixed values of rho. Okay, now I have not explained at all how those specific couplings show up, and that's my next step. Okay, right now I'm just classifying them in terms of their derivatives, so I can have an organizing principle to describe them. Okay, good. So that this is really just classifying things based on numbers of derivatives in a sensible way. Now let's classify them based on an amplitudes principle, which is called soft behavior. Okay, and the kind of upshot is this. It's very intuitive. In this picture, if you wanted to probe the non-linearly realized symmetry, of course, you can just take the Goldstone boson and you can kick it around in a circle. Okay, but famously, if you give the Goldstone boson a VEV, it is effectively the same as kind of shifting your a vacuum around this basin. Okay, so there's this of course famous statement that a very soft pion is just kind of taking you across this circle. Okay, you could probe the moduli space with soft limits. Okay, so that tells you that non-linearly realized symmetries are encoded inside the soft behavior of amplitudes. So let me again formalize that and turn this into a bootstrap problem. So we have some amplitude A of P. We can send P goes to 0, which is the soft limit, which is taking its energies and momentum to 0. And I want to define a soft parameter sigma, which is just the power with which this thing goes to 0. Okay, so if you like, it's a generalization of what I wrote before, where sigma is not necessarily 1, but it could be larger than 1. Okay, and I'm going to call that the soft parameter. Okay, now if we just study that setup, okay, we can ask, for a given theory, what should we naively expect for sigma? Okay, now just intuitively, if I give you a theory with 1,000 derivatives on the field, then you would reasonably think that sigma would be 1,000. Okay, if you have tons of derivatives acting in your fields, you should expect more and more powers of P. Okay, so roughly speaking, these rows here are counting number of derivatives of fields. So when rho is huge and sigma is small, that should be very easy to accommodate, because when rho is huge, you have huge numbers of derivatives on every single field. When sigma, if that's much bigger than sigma, then that should be easy. But the opposite limit is confusing. Let's say rho is very small, but sigma was huge. That is to say, you have not that many derivatives on each field, but sigma was enormous. Then something confusing happens. Okay, so let me or non-trivial needs to happen. Okay, so let me put that into equations. Sigma kind of automatically is going to be less than or equal to the number of derivatives per field, just manifestly. If every vertex just has some number of derivatives per field, then sigma will accommodate that. And you can see that as n goes to infinity, looking at amplitudes at infinite number of particle scattering, then this thing is actually rho. Okay, so sigma is naturally less than or equal to rho, okay, without doing any work. So if someone gives you a rho as 1,000 theory and you find sigma is 7, you're like, okay, nothing surprising here. 7's less than 1,000. Now, the opposite limit is instead very confusing. If someone gives you a theory with only 7 derivatives per field and somehow amplitudes vanish with 1,000 powers of momenta, that's very confusing. Okay, it's not generically expected. Okay, what that means from the point of a bootstrap is that if we enforce this condition, we demand that this is true. That is to say, if we demand the condition of enhanced soft behavior, softer behavior of amplitude than you'd expect given the Lagrangian, then we should expect this to non-trivially constrain the theory. Okay, so that's what I'm going to do now. I'm basically going to assume better behavior than you would expect and see what pops out. Okay, that's our game. Demand that amplitudes vanish more quickly than their vertices appear to allow for, and then see what that implies. Now, of course, the upshot is that when we see something like this will not vanish sufficiently fast. This will not vanish sufficiently fast, but the two together can vanish sufficiently fast if there's a relationship between their couplings, okay, which is exactly what a non-linearly realized symmetry does. Okay, so we're going to kind of reinvent that concept from the point of view of amplitudes. Okay, so let's do this soft bootstrap. Okay, so we're going to assume that sigma, which is the degree of vanishing of amplitudes, is greater than rho, which is approximately the number of derivatives per field. Now at 3 point, there's no amplitudes at all, which we discussed last time, so we can jump straight to 4 point. Okay, and just ask, what are the soft properties of a 4 point amplitude? So here, we really did this exercise before also. We can write down a completely general 4 point amplitude, okay, for any scalar theory. It's just some number of powers of S, powers of T, and powers of U, where the powers are A, B, and C. But if I want to fix to a given row, okay, so one thing I should say is that I'm imagining for this bootstrap fixing a row and then fixing a sigma and then seeing if there's solutions. Okay, so this is like me fixing the spin of a particle to be 2, fixing its mass to be 0, and seeing if there's an S matrix. Here I'm taking a scalar and fixing it to have some number of derivatives, demanding that it has some soft limit and seeing if such a theory exists. Okay. Now, what that means is that a plus b plus c is not arbitrary. It's constrained to be rho plus 1 because the total number of derivatives has to be rho plus 1 in this theory, okay, to be consistent with the theory with some fixed rho. And what you see is something very nice, which is that S goes, let's say, as P1, T goes as P1, and U goes as P1. Okay, so if I just take P1 goes to 0, then this automatically scales as P1 to the rho plus 1. Okay, so if I just take the soft limit of any scalar amplitude of any type, it goes as rho plus 1. Okay, in the limit of P1 is soft, the amplitude vanish with rho plus 1 powers of rho of P1, which means that sigma is rho plus 1, which is of course greater than rho, which means there's already an enhanced soft behavior. Okay, so 4-particle scattering is automatically enhanced in this language. Okay, this happens to be just kind of a amusing miracle at low point, but the point is that everything has a surprising soft limit if you just look at 4-particle scattering. Okay. Now, as you might imagine, the flip side of that is that the soft structure is completely unconstraining because this matrix of couplings is completely unconstrained, right? This could be anything. Every amplitude has this property, so I learned nothing at 4-point. Okay, so we've learned still nothing at 3-point and 4-point, and we've determined that the soft bootstrap that we're looking at has no constraints at all. Now, of course, what this means is we have to go to higher point. Now we could go to 5-point, but for kind of ease of discussion, let me assume a theory with a Z2, which is true for the Carl-Lagrangian with G parity and with many, in fact, all the theories that we'll be interested in. So let me just jump to 6-point. Okay? So I'll be interested in theories where there's some 4-point that I start with, and then the next non-trivial operator is at 6-point, okay? And otherwise all even point. Now here's the procedure. I'm going to spell it out in words, but hopefully the tools I gave you from last time are sufficient for you to kind of just do this exercise. You know, assume some rho and sigma. Just pick them. Okay. The idea is you assume something about rho and sigma and see if an S matrix exists. What you do is you build a 6-point function as an ansatz. So this is an ansatz polynomial in pi.pj, which I told you how to build last time. There's some set of 6-particle Mandelstam invariants, a minimal basis. Just write a totally general function of those, okay, with free coefficients. Now, there's a factorization piece, which we can build from these kind of factorization diagrams, just like before. And here we plug in A4 that we built previously. A4, you know, of course, we have no idea what these coefficients are, so you just leave them unfixed. But you plug in A4 here and here, and then this is your factorization piece. Okay, so the point here is that those A4s will correspond to a given row, which depends on, you know, how many total number of derivatives are in this function. Okay, but the point here is that this thing is kind of uniquely fixed by lower point, and then this thing here is an ansatz. Okay, now you go to your minimal kinematic basis, and then you take the soft limit and just demand this constraint. Okay, now what that's going to do is it's going to relate these things together, so they have to destructively interfere in order to make this condition satisfied. And what you get is a very rich structure of theories. Okay, so you know, just let me just recap maybe before jumping into it, like what happens if you demand sigma to be too high, you find that you get no theories. Okay, but if sigma is large but not too large, you can find and rediscover old theories as well as derive and learn about new theories. Okay, so let's just go through this bootstrap one by one. So let's say I take rho and sigma is 0 and 1. Okay, so in other words, you can think of this as I'm picking rho as 0, and then I want to pick some sigma that's larger than 0, so I pick 1. Okay, again, I'm not going to do this bootstrap because this is actually done long ago, you know, literally decades ago. But let's say you took some theory with flavor. Okay, I want to be general, so I add flavor indices and I add completely general flavor structures. And then I enforce that this 2-derivative theory vanishes. Okay, so in other words, I have like a d phi, and then everything else is a function of phi here. Okay, now you shouldn't expect generically for the amplitudes to vanish with 1 power of p because there's no p here. Okay, there's no p sitting in front of either of these phi's. Right, the p's only sit in front of these d phi's. So not every field has a derivative in front of it. So it's actually surprising for any amplitude to vanish with 1 power of p. That should be surprising. But what Susskind and Fry showed ages ago, which is that if you just build and bootstrap up this constraint and ask what the coefficients you get are, you literally derive the nonlinear signal model for a symmetric coset space, an arbitrary symmetric coset G mod H. Okay, so in other words, you can think of kind of 4-point as dictating your kind of leading Riemann curvature of your field space, and then everything else is dictated from that. Okay, it's a very interesting paper by them, but this is really the original bootstrap. Okay, said in kind of more classical language, the statement is if you assume the Adler zero, which is this condition, then the NLSM is the unique scalar theory with 2 derivatives, which gives an Adler zero. Okay, so it bootstraps the NLSM, and we can build it without knowing about chiral symmetry breaking at all. Okay, now we can keep going. Okay, so let's go up one more order. So let's say we define a theory that has 1 derivative per field, so d phi, d phi, d phi, and I imagine that these are completely arbitrary coefficients, lambda 4 and lambda 6, okay, and lambda 8 and so on, okay, and so on. And I demand that sigma is 2. Okay, now before, we saw that there was 1 derivative per field. So if A vanishes with 1 power of P, that's not surprising. But if it vanishes with 2 powers, it's surprising. Okay, now what happens when you do this bootstrap? Well, you find that lambda 6, 8, 10, 12, everything is actually all related to the leading coupling. Every single coupling is related to the first one. This is lambda 4 squared, lambda 4 cubed with fixed numerical coefficients. Okay, so in other words, demanding this gives you a theory for which this sum telescopes into this interesting square root form. The square root of 1 minus d phi squared, which to the uninitiated might seem odd, but it's actually the Lagrangian for Dirac-Born-Infeld theory. Okay, so if you don't know about this theory, it's a theory which corresponds to a phi, which labels the coordinate of a brane moving in a 5th extra dimension. Okay, so imagine I add some flat 5th extra dimension and I call the coordinate phi. Then the action corresponding to the motions of that brane is this Lagrangian. You can really think of the square root as basically a gamma factor. Okay, and phi here is really a coordinate. Okay, and the fact that phi can vary with space-time, with our 4-dimensional space, is that the brane can wiggle in 4D space-time. Okay, in addition to moving in the 5th dimension. Okay, now of course I didn't assume any of that backstory. I'm not assuming string theory here or an extra dimension and so on. The point here is that this simple condition of the Soft theorem told me about this structure. Okay, it pops out of this theory, and in fact, this DBI, Dirac-Born-Infeld, has a non-linearly realized symmetry, which is very physical and very easy to understand. Which is that if I give you some phi which labels a brane in the 5th dimension, it doesn't just have a shift symmetry. That is to say, you can take the brane and translate it in the 5th dimension. That would correspond to phi goes to phi plus c. Okay, that's a translation. But you can also rotate it in the 5th dimension. Okay, you can boost it. And that set of boosts in the extra dimensional coordinate is precisely a non-linearly realized symmetry that this thing has. And that's, of course, been long understood. This is an old story. But the point is that this soft limit just implies it. Okay, so a way of just relearning about extra dimensions, about boost symmetry in another dimension, is to just demand this constraint. Okay, without any of the backstory of where DBI actually came from. Okay, now we can keep going. Okay, I'll go one more step. We can set rho to 2 and sigma to 3. So this is a theory that has many derivatives, asymptotically 2 derivatives per field. So there's many derivative structures. You could write down an ansatz with every single structure, and then demand that amplitudes vanish extremely softly. In the soft limit, they vanish with 3 powers of p. Now, this thing at the time actually didn't have a name. It was just an amplitude with this bizarre feature. Okay, so only afterwards, only after the amplitudes was discovered was it given a name and an understanding, which was the special Galilean, which it was realized that it was a version of a so-called Galilean theory that has a higher order shift symmetry. Okay, so if you gave me a scalar theory with an crazy high shift symmetry, okay, so five shifts here by a constant, which is the usual U1 Goldthunberg shift symmetry, but also can have this linear in X symmetry, which is called the Galilean symmetry. And then on top of that, an even crazier doubled symmetry, which is the special Galilean symmetry. And this is an insane amount of symmetry. This uniquely fixes every single Lagrangian term in such a theory, and that's called the special Galilean. Okay, and I'm telling you this backstory just to kind of emphasize this point, which is that this special Galilean was first found in amplitudes, okay, through soft limits and actually through other constructions than a CHY, but it was an amplitudes object before it was given a name and a symmetry. Okay, so it's a much less impressive version of how string theory was discovered, where string theory was famously discovered through the Veneziano amplitude and Virasoro-Shapiro. But this is just an example of like a legit symmetry being not just rediscovered, but actually, if you like, discovered through this path. Okay, so this is a way of finding symmetries in the abstract without ever writing the Lagrangian. Okay, I'm writing the Lagrangian for you so you can kind of better understand it. But the entire mechanics of this bootstrap was just functions. Okay, as I said, it was just building a function, you know, building this function and finding solutions. Okay, good. Okay, so with this all said, we can build a map of this theory space. Okay, the various theory spaces I've described. Okay, so we last time we looked at the theory space of spinning particles with Lorentz invariance and factorization, where this is the spin of the particle, and this is again rho. This is the same rho parameter I mentioned. So as I said, Yang-Mills has rho of -1 and Giroux has rho of 0. And we saw that you know, there's a unique unique spinning theories with spin 1 and spin 2. I didn't explain actually why higher spin aren't included. That has to do with couplings to the stress tensor, but in just general grounds, there's kind of excluded regions and allowed regions. Okay, so this, if you like, was the original Lorentz factorization, and I should also say plus stress tensor bootstrap, which tells you that theories that describe the world we live in live on the kind of boundary of existence. Okay, so this in and of itself is kind of an interesting statement. Yang-Mills is a one parameter theory with alpha S. GR has G Newton. Phi cube theory has just the cubic operator. Of course, you could argue this even shows up in the standard model through the Higgs cubic coupling after below the electroweak symmetry breaking scale. But what's amusing is that, you know, these are all elements, if you like, the standard model, and they all have the property that they live on the boundary between being allowed and not allowed. Okay, and in hindsight, that's kind of obvious why it had to be true. Yang-Mills has one parameter. If you took Yang-Mills and tried to constrain it more, it would then be excluded. Okay, so these are kind of just marginally excluded theories. Any additional constraint that you impose on these theories is dangerous because it can immediately exclude them. Okay, which is why they're special and why they have very few free parameters. That's just to say one free parameter for all of them. Okay, now of course there's other junk in here which has more free parameters, and that includes higher dimension operators, theories with many coefficients, and so on. Okay, but these have a special place because they're at the boundary of existence. Now, what I've shown you here is that this bootstrap with soft has a similar property where I plot here not spin, but the soft property, and we have pions, dBA, and Galileans. Of course, only chiral Lagrangian shows up in the standard model, but these guys show up in cosmology. And it's a very similar map where I didn't explain this either, but kind of things up here are also excluded by consistency. Okay, in fact, the soft bootstrap eliminates all these pieces here. Okay, so there's kind of this is the kind of general picture I want to kind of suggest here, which is that, you know, this is different from writing a Lagrangian. This is writing an amplitude, which is a function of kinematic variables, which depends on just, you know, parameters like spin, numbers of derivatives, and soft behavior, and then just cutting out the allowed space. Okay, and we can learn things like which theories can even exist in principle. Now, what I want to talk about in the kind of last 20 minutes here, this is actually going to push me into the next lecture, which is what I want, is that, you know, in some sense, we're still relearning facts, right? Here we're, you know, we know about these theories, at least these were known here. We could, in some cases, discover new things, but, you know, to 0th order, we're still rediscovering. Okay. What I want to talk about from here on in my set of lectures is how we can now learn by studying these particular theories, things that look very, very non-trivial from the point of view of QFT. Okay, And that's really going to have to do with connections between all of these theories. Okay, so like gravity, Yang-Mills, phi cubed, and then Galileons, dBi, and pions. Okay, these are not things that normally are said in the same sentence. We built them all through kind of similar bootstrap methods, but these are inextricably connected in a very direct way. Okay, that is to say, pions and gravitons, pions and gluons, phi cubed and Galileons, they're actually really closely connected in a very direct way, which I want to describe, and which I think is only really obvious because these things show up all together and they keep showing up in all these amplitude stories. Okay, if you just open up Amplitudes papers that talk about scalars, gravity, and gauge theory, these amplitudes just show up and they're just nice and there's some connectivity to them, which I want to tell you about now. Okay, again, any questions? Maybe here's a good breaking point if you have any questions about kind of the soft bootstrap, because I'm going to move on to this, connectivity between theories. But otherwise, let me just push forward, or you can ask at the end. Okay, so with that, let me move on to unity of scattering. Okay, so as I just said, the theories that keep appearing here are secretly connected and they're unified. Okay, and I'm going to use the word unification in the more colloquial sense. Okay, but I do really mean unified in a really concrete sense, just not the one you're kind of used to if you're in phenomenological circles. Of course, the usual picture from high energy physics of unification is you have some SO10 gut that could break to SO5 or Patty Salam, and then ultimately through some breaking pattern become the standard model. But going from top to bottom here means going from high energy to low energy. Okay, the dynamics spontaneously break gauge symmetries and bring you down to low energies, where kind of at the bottom, all you're left with is fragments of some kind of beautiful, symmetric structure which has been shattered. But if you go to high energy, it's all restored in some beautiful way. Okay, so the picture here is that energy is the vertical axis. Okay, now in amplitudes, there is a similar, I shouldn't say similar notion of unification, I should say different notion of unification, which connects all the amplitudes that I've already discussed super directly. Okay, and it's the following. Okay, so this is instead my picture where like the analog of like the SO10, the master gut is gravity, and Yang-Mills theory, Born-Infeld theory, Dirac Born-Infeld theory, pions, Galileons, phi cubed are all, if you like, descendants from this bigger theory. Okay, now I want to emphasize here, I'm not saying that you can take a gravity theory at super high energies, give it some vevs and get this stuff. I'm not saying that, because the vertical axis is not energy, it's spin. Okay, hopefully you can see here that this top line is spin 2, this second line is spin 1, this last line is spin 0. Okay, if you also look closely at this plot, you'll also realize that the number of derivatives is increasing as you go to the right. Okay, phi cube theory has no derivatives, Yang-Mills has a couple more, gravity has more derivatives, Born-Infeld has even more, and the Galilean has tons of derivatives. Okay, so roughly speaking, number of derivatives, which was rho, is going to the right here. Okay, now here's my statement of unification. Let's say someone, some oracle who just knew all things, handed you the tree level S matrix for gravity. Okay, that is to say all graviton scattering amplitudes. In fact, I need to maybe amend that to say a generalized version of gravity where I don't just have gravitons, but also dilitons in 2 forms. Okay, that's going to be important later, but let me just say, strictly speaking, let me talk about the theory, which is effectively the 0 modes of the closed string. But what it is really just gravitons coupled to dilitons in 2 forms. Let's say someone gave you the full S matrix. So let's say someone just handed you this S matrix. Okay, they give it to you, let's say at tree level. The statement I'm going to show you in this 15 minutes and maybe the beginning of the next lecture is that from this object, you can sculpt out every single other amplitude. Okay, every other amplitude can be built and extracted from this graviton amplitude. Living inside the graviton S matrix is the Yang-Mills S matrix, the pion S matrix, and all these other exotic S matrices in some very clean way, which I'll show you and even give you some examples. Okay, so my mantra for this, and again, this is, I should say, it's like in the end, a really trivial amplitude statement ultimately to prove and show, but from a field theory perspective is really, at least to me, bizarre and strange, okay? Especially when you see the mechanics of how to do this. The mantra I want to give, and I give for this, is that gravity is the mother of all theories. Given the tree level S matrix for graviton, dilaton, and 2 form, you can sculpt out all other S matrices with actually a very trivial set of operations, okay? Let me show you what I mean by that and derive it. It's not a magic trick, it's something we can actually derive. Okay, and we're going to use the kind of kinematic notions that we talked about last time in terms of d-dimensional Mandelstam invariance. Okay, so everything I'm going to say is in d dimensions, as has been this whole set of lectures. Okay, so imagine we consider Yang-Mills amplitude, which has a bunch of polarizations, E1 to En. It's a function of P.P, P.E, and E.E. Okay, and as usual, I assume on-shell conditions. Okay, now last time I assumed a minimal basis for these. I'm really not even going to have to assume that here. Okay, so if you like, compute A in any way you like, and then write it in terms of this. You could use Peskin and Schroeder. It doesn't matter. Take any formulation you want. I want to be maximally agnostic. So you don't have to massage anything in any way. You just have to make sure you assume on-shell conditions. Okay. Now, the idea is I'm going to turn statements I made previously into differential operator statements. Okay. Now, one thing that we used very heavily last time was the word identity, which is that if you take the amplitude and you set the polarization equal to Pi, which I'm going to call an operator, Wi, that is to say the ward identity on leg I, then I needed to annihilate the amplitude. Okay, that's the ward identity. And I'm going to define a differential operator that does that. Okay, so what does this differential operator do? Okay, let me kind of unpack this briefly. It's a differential operator. What it says is, you treat your amplitude A as a literal function of these scalars, these scalar Mandelstams, which means I can differentiate with respect to a Mandelstam. That's what this DD object is. I'm differentiating with respect to the Mandelstam V.ei, where V could be Pj or Ej. Okay, so if you think about what this operation is doing, it's basically, looking at every possible Mandelstam that contract with Ei. Ei could be contracted with Pj or Ej. It's removing it and then it's replacing it with Pi.v, which is just replacing Ei with Pi. Okay, so this is just a heavy-handed way of doing this replacement, but it's doing it as a differential operator. Okay, so in other words, if you take this differential operator, it will annihilate the amplitude, no matter which way you compute it. That's just the word identity. Okay, now let's introduce a little more machinery. I want to introduce a notion of total momentum conservation. Which of course normally seems trivial, but I want to introduce an operator for it. Okay, what is the operator? I'm going to call this PV, and all it is the sum of Pi.v. Okay, Pi.v is a Mandelstam, and the statement is just that the sum over all I is something which should annihilate the amplitude. Okay, of course we normally think of this as just a number or function, but it still annihilates the amplitude. Okay, so I want to think of this very formally as two operators, Wi and PV, which annihilate the amplitude. Here, Wi initiates the ward identity for leg I. Here, PV says that momentum is conserved. Okay? And here, a V can be anything. Okay, in case it wasn't clear, every time I write a V here, the V is summing over any possible d-dimensional vector. Okay, so these are just differential operators. You can compute their commutators. Obviously, some of them are trivial. So P commutes with P because it's just a bunch of numbers. The ward identity commutes with itself. That should be clear too, because if I set E1 to P1 and then set E2 to P2, I could do it in the opposite order and it doesn't matter. Okay. But you can also take this commutator, which is not 0, but it's proportional to P, which annihilates A, so it's effectively 0. Okay, so in other words, this doesn't commute, but it commutes up to something which is total momentum, which still annihilates any amplitude which this whole set of operators act on. So it's effectively 0. Okay, so you can probably see where I'm going with this. I want to abstractify, the basic primordial things that constrain the amplitude in order to learn more about them. Okay, so why did I introduce these objects? Well, I want to introduce a notion which I'm going to call amplitudes transmutation. Okay, and the logic is the following. Let me try to derive an operator T, which I'm going to call a transmutation operator, that commutes with both of the operators I just talked about. Okay, so T commutes with ward identity and T commutes with momentum conservation. Okay, so let's say you find some t that does this. So if this is true, then if you act t on an amplitude, okay, so let's say you act t on an amplitude, giving me a new object called TA, then this thing actually is also gauge invariant, because if you act on with WA and then commute the 2, then you still get 0. And similarly, P also annihilates TA. Okay, so what I'm saying is that this object TA, which I'm calling the transmuted object, satisfies the ward identity and also conserves momentum, provided T commutes with these objects. Okay, so this is just a fancy way of saying I want to build a set of operators T, which take gauge invariant momentum conserving objects and build new gauge invariant momentum conserving objects out of them. Okay, so let me kind of briskly go through how to generate them, derive them from first principles. So you can just write an ansatz for what T is, a general differential operator, right? So I'm taking a derivative here. I'm assuming it's a first differential operator. Okay, that's just an input. And here I assume AI, BI, A, B, and C are just functions of these Mandelstams. And I just demand that this T ansatz satisfies this commutation relation. Okay, it's just an exercise in commuting, differentials. Now, there's actually many such operators that do this, but let me show you a set of them which are very remarkable, which I'm going to call transmutation operators. Okay, and hopefully this is not too mysterious. Okay, I've given them more subscripts. Okay, so if you like, this is my definition of a bunch of operators, but all they are differentials. Okay, so this Tij literally says take an object and differentiate with respect to ei.ej, the Mandelstam invariant ei.ej. This guy says differentiate with respect to pi.ej, and then subtract the derivatives with pk.ej. And then this so on and so forth. This does even more complicated things. Okay, now the statement is, my claim is that these things all satisfy these commutation relations here. Okay, so they produce gauge invariant objects of muons. And in fact, the objects they produce are new amplitudes with different particles in them. Okay, so I'll show you how this works in explicit examples. But what this operation does, this first one does, is it takes a theory with an amplitude with 2 gluons. That is to say, I and J are both gluons, and it replaces them with scalars and gives a gauge invariant amplitude where I and J have become scalars. Tijk is something which, in kind of a more interesting way, takes a single gluon and replaces it with 1 scalar. And by far the most bizarre case of all is this last one, which takes a gluon and replaces it with a pion. Okay, now that should sound totally crazy from what you know about QFT. So I should emphasize here, I'm not saying anything about the strong coupling limit of Yang-Mills and glue balls somehow being equal to the chiral Goldson bosons that come from spontaneous breaking of flavor symmetries. I'm not saying that at all. I'm saying literally pure Yang-Mills. You can extract from it pion amplitudes through this differential operator. Okay, so hopefully this conveys to you that these are just differential operators that act on any representation of the amplitude you like. In fact, let me kind of combine them into more natural objects. So let's say I don't want to just transmute one set of gluons. I want to transmute all of them. Okay, just to make things a bit simpler. I can define some object T and L, which takes a total set of n gluons and replaces them with scalars, or takes an n set of gluons and replaces them with pions. Okay, I'm sorry. This is a typo here. This should have an L. So yeah, this L here should be here. So this is a typo. Sorry about that. But the point here is that there's some set of operators T and L which do this transformation. Okay, and I mean this like really super explicitly. Okay, so let me tell you. I'll show you an example in a second, but let me show you the global picture first. So take a Yang-Mills amplitude, compute it in any way you want. Okay, this could be the 4-point amplitude we computed, last lecture from the bootstrap. But you could take your Peskin and Schroeder's Feynman rules and just compute Yang-Mills. You can use anything you want actually. Okay, but the statement here is take those amplitudes. I should be more precise here. Take the color ordered amplitude. Okay, if you don't know what that means, you can ask me later. But basically, that means that you can take an amplitude which has many different color structures and decompose it into its kind of independent color structures, and pick out one of the independent color structures, and that's called the color ordered amplitude. You can compute that, and then apply those differential operators I said above to get the amplitudes of pions and the amplitudes of phi cube theory. Okay, this BAS here is bi-adjoint scalar theory. This is the kind of first time it showed up. And it's to a phenomenologist is a very strange theory to consider, but in amplitudes is everywhere. I'm sorry, I have a typo here. But the idea is that the scalar field is an object which has two color indices, a barred and unbarred color index. So sorry, there should be an A bar here and a B bar there. But just focus on this. These are scalars that have two color indices and two color structure constants. But it's a phi cube theory. Okay, so this is phi, phi, phi. It's ultimately just a cubic scalar theory. Okay. The statement is you can take Yang-Mills and you can get amplitudes in a phi cube theory. You can also take Yang-Mills and get the amplitudes of pions at any endpoint. Okay, and again, this is proven. This is not a conjecture. This is just a fact about all amplitudes for any number of scattering at tree level. Now you can go even crazier here. Okay, you can take graviton amplitudes and do the same thing. Okay, so you can take graviton scattering amplitudes, and by that I mean including dilitons in two forms. Whereas before you can split, as I said before, you can take this this object and split it into E and E bar, and apply these differential operators, and you get Yang-Mills. So you can take gravity and you can get Yang-Mills. Okay, but you can also get gravity and go to Born-Infeld theory, which, if you don't know, is another theory that shows up as a nonlinear extension of QED. Okay, Born-Infeld theory is basically a very special version of the Euler-Heisenberg-Lagrangian with extremely nice properties. Okay, this is again just kind of a magic trick. Just differential operator gives us these these theories. You can keep going. You can take Born-Infeld and you can hit them with differential operators and get pions and Galileans. Okay, so I'll return to this kind of web of connections in a bit, but let's just see how this works in some super quick examples. I'm going to try to make it on time today. Maybe this will be 5 minutes late. The idea is, let's say you take a Yang-Mills amplitude and you want to get phi cubed. So I'm literally saying take your Yang-Mills 4-point function that we wrote last time, hit it with the differential operator I wrote above, and you get 1 on S plus 1 on T, okay, which is the color ordered phi cubed amplitude. Okay, it's missing a U channel because it's color ordered. That's some detailed thing that doesn't matter. But the point here is that for the color stripped amplitude, this is exactly the right amplitude for phi cube theory. You can do more exotic things, like you can take Yang-Mills and go to pions. So take a gluon amplitude, hit it with a differential operator, and you get this, which is S plus T, which you'll notice goes precisely as order P squared, which is how pions go, and it's exactly the correct pion amplitude at 4-point. And of course, you can go to higher point, but I'm not going to do that here. You can do more exotic things, which I'm not going to talk about here, but you can also take kind of combinations. You could take 2 separate transmutation operators. This is a particularly simple example, but you can take Yang-Mills and you can get amplitudes in scalar QCD. Okay, so this is an amplitude for a scalar coupled through a gluon. Okay, you could call it scalar QCD or scalar QED, and this is the correct amplitude for that. So there's like a huge class of amplitudes you can get, where if you just start with gravity, you get Yang-Mills, and from Yang-Mills, you can get everything else. Okay. Oh, good. I'm going to finish, I think, exactly on time because I did this a little bit fast. But this is kind of the upshot of this connectivity I was saying. Okay, someone hands you the gravity amplitude at endpoint, and by taking derivatives with respect to Mandelstams, you can get every other theory. You can go from Yang-Mills down to phi cubed, or you can, if you like, take a detour to NLSM. There's multiple paths to the same theory. Okay, so you can get NLSM in 2 different ways, or you could go all the way this way. Okay, but the point is, by just taking different sets of differential operators, you can generate all the S matrix for any number of scattering, any number of particles in all these theories. Now, of course, a very natural thing to worry about now. I mean, so first of all, this is just a cool structure. Okay, like you could ask, like, why is this true? Okay, I mean, I showed you kind of mathematically why it's true, but why does gravity contain pions? Okay, if I told you the graviton amplitudes, you know, if you like polarized in some very bizarre way are pion amplitudes, that would be confusing, I think, to the vast majority of people who hear it. Why do special Galilean amplitudes show up inside gravity? Okay, now the way to maybe even sharpen this even more extremely is to realize that some of these theories don't even make sense. The Galilean amplitude, which I think maybe Eugene has, or will talk about if he talks about positivity, is something which violates classic Wilsonian positivity bounds from analytic dispersion relations. So in other words, it is inconsistent with UV completion and can never come from string theory as a statement of principle from IR bound, from IR consistency. And yet it still descends from gravity from the set of operations. Okay, so these are all kind of strange bedfellows, and it's not really clear why they're all here together. So that's one thing I want to maybe briefly address next time, which is like, why is any of this true? But maybe a good segue into next lecture is to ask about the practicality of this, which is, well, great. If an oracle gives you gravity, you're in good shape, but gravity is hard. So what if you don't have an oracle? What if I only have the stuff in the bottom, okay? And I want to go up, okay? And thankfully, in this case, it turns out that we have a way of going up this ladder. Okay, and this is something that I'll talk about at length next time, which is called the double copy, where you can take Yang-Mills and gauge amplitudes, and through a similar, well, not similar, but a different operation, get gravity amplitudes from them. Okay, you can go up, if you like, instead of differential operators, these are like integrations to go upwards. And similarly, you can write down an LSM to go up this way. Okay, so there's a way of double copying, which is this terminology of kind of taking theories with color and kinematics and kind of going up in this direction. I'll make that more precise next time. This is a way of actually getting gravity amplitudes also for free. Okay, and the kind of practical upshot of that is that 50 years, maybe 60 years of research in QCD has helped us compute this extremely well. We can use that to upgrade to gravity trivially and learn about every other theory as a byproduct. Okay, and I'm going to unpack that some elements of that in my last lecture next time. But maybe I'll stop here again just to end on time, and I'll take questions. Thank you.
Thank you very much. Any questions from the audience? Yes.
When rho is more than 1, it means a higher dimensional filter P. Does it mean that locality is violated?
Good question. Good. So let me just first closely litigate even the first statement that when rho is greater than 1, you have higher derivative pieces. Even when rho is equal to 1, you have higher derivative in the sense that there's one derivative per field. So it's still a non-renormalizable theory if there's one derivative per field. But if you're worried about the extra derivatives, like more than one derivative per field, so if you're worried about, for instance, as soon as you have a theory with more than one derivative per field, the initial value problem is confusing. You generally have ghosts. You should totally generically worry about that. In a general theory that has many derivatives on a given scalar field, you should expect an Ostrogozzi ghost to appear. What's very remarkable is that in these Galilean theories that pop out of this, they are precisely theories in which those ghost modes decouple. Okay, so they're a little bit like Lovelock theories in gravity, or like the analog is like a Gauss-Bonnet is the kind of simplest example, which is like you're adding more derivatives, and yet somehow ghost modes don't appear. And it has to do with the usual kind of epsilonology where, at least if you fix dimensions, it looks like a certain conspiracy which removes those modes. But yes, very generally, if you just randomly pick a rho equals 20 theory, you should expect ghosty modes, and you would worry about ghosts for sure. And again, I would kind of still say what I said last time, which is that if you're rightly a completely responsible physicist, you bootstrap the amplitudes and then make sure those ghost modes decouple, and then you get Galileans independently, and you learn about them by removing those modes. But if you have maybe lower standards and just, I have ghosts, I'm not worried about them, you can still bootstrap them up. Okay, you can just input whatever principles you want. Of course, personally, I wouldn't want to have the ghost modes myself, but you can input whatever you like. Does that answer your question?
Any other questions? Let me ask one question about the earlier part of your lecture today on the scalar amplitude. So you talked about nonlinear chiral Lagrangian part, and you discussed the 4-point function, 6-point function, etc. But in the real chiral Lagrangian for the hadronic world, there is also 5-point function from the best-similar interaction. And how do you introduce in your program?
Great, excellent question. So we actually included that in another paper. So you just add a 5-point function and allow for epsilons. So yeah, you just add it. So I took the G parity conserving case, but if you add the that 5-point interaction, then you can still bootstrap it, and actually also has nice soft properties. So that's actually another point on the plot that I didn't write, but it requires going to odd point and adding kind of a more involved kinematic invariance. But actually in this set of papers, we actually talked about precisely that term. Yeah, and its general dimensional analogs. Yeah, but you can absolutely include it. Yeah.
Any other questions?
I have one question. So from your diagram, when you apply these operators to gravity, you generate Young-Mills or Born-Feld, etc. Are these just examples? Or is this a complete list of the different theories you can generate, or are there more complicated theories you could also obtain?
Right. Very good question. So that is the exhaustive list in terms of the theories that show up the most in amplitudes, because I won't get into this, but all those theories show up in all these other interesting formulations like associahedron, amplituhedra, and CHY. Like they just keep showing up. Okay, but you could just ask in a more general sense, like with this set of differential operators and the full class, what else can you get? And honestly, we just haven't explored all of them. I can give you an example. So there's a whole set of differential operators I didn't even mention, where there's no polarizations at all. Okay, so all the differential operators I wrote had like EIs in it, but there's a set of differential operators that just have P's. It's like derivative of Mandelstam, basically, times a Mandelstam. And those are also completely fine and would be consistent with gauge symmetry. Now, they do strange things like they take simple poles and they turn them into double poles. Okay, but one thing I've wondered is whether it could give an exotic theory like Weyl gravity, where you have you expect p to the 4th type propagators. But yeah, there's a whole possible web of other things, and I haven't thought about this story in a while actually, and I just hasn't been explored. But in principle, the general statement is, if you really build the full class of transmutation operators that are consistent with those commutation conditions, that is a complete set of objects which generate gauge invariant things from other gauge invariant things. Now the question is whether the new gauge invariant things are amplitudes. That's non-trivial, because there's many things that it could be, right? I could take an amplitude and take it to the 7th power and subtract another amplitude, and that would be gauge invariant, but not an amplitude. It's some weird object. The kind of miracle is that small miracle is that the differential operators I showed you don't just give any old random gauge invariant. It gives you an actual amplitude in another theory. And this is just my long-winded way of saying I don't know what the full space is. There could be others. I literally haven't tried applying. I mean, I don't think anyone's tried applying it to more general theories. No.
Okay, thank you.
Thank you for your nice lecture. I have a question on your comment on the gravity as a model of theories. Apart from gravity, you added dilaton and two-form field in order to complete the theory, probably. So can you comment on that? And why do you need dilaton and two-form field other than gravity?
Excellent. Yeah. Like, why did I even need this? Yeah. So let's think about. Here's the technical reason. Okay. So in this theory where there's a two-form and an axion, in addition to the graviton, you can think of the polarization tensor as not being epsilon mu nu, like a symmetric tensor, but you can think of it as epsilon mu nu bar, which is the general d by d matrix, right? So in other words, like when you add the two-form and the dilaton, it gives you like the trace and the off-diagonal pieces of a general d by d matrix. Okay, and what that lets you do is take epsilon mu nu and write it as an outer product of an epsilon mu and an epsilon tilde nu. Right. So in other words, for a symmetric graviton, I can only build that from a symmetric product of two vectors. But for a general D by D matrix, it's an arbitrary product of a polarization E and another polarization E bar, or E tilde, or whatever I called it. So what this theory allows you to do is write a graviton amplitude in terms of epsilon mu's and epsilon bar mu's. Okay. Now, why did I need this? Well, these differential operators, they act on either E or E bar. Okay. So the idea is the following: you take a graviton plus dilaton plus axion amplitude that has E's and E bars, and I act with a differential operator, but where the differential operator takes derivatives with respect to E, not E bar. So E bar is like untouched, but E is hit upon, or vice versa, depending on what your conventions are. But the point is, you kind of differentiate with respect to one side of the polarization, not the other. And in that case, you get Yang-Mills. Now, that's the technical reason why you need it. But I think the overarching physical reason is that the web of theories that you build here, when you build gravity from the theories on the bottom, the natural theory you get is not gravity, but a bigger theory, which is gravity plus dilaton plus axion. And that has to do with, again, in fact, you can do this even with the bootstrap. I think I mentioned, I did last week. Last week, I wrote down a bootstrap that had an epsilon mu nu, two index symmetric tensor, which was the graviton polarization. If you replace that with e mu bar and did the bootstrap, that is actually the 3-particle amplitude for two-form dilaton graviton theory. Okay, so quite literally, if you take Yang-Mills as a function of epsilon, Yang-Mills as a function of epsilon bar, and just take their product, then that thing actually has the two-form and the dilaton inside it. So there's just a natural sense in which by kind of not making the two epsilons the same, you just get the whole multiple for free, and it's a natural object that shows up in all of these structures. Yeah, hopefully that answers your question.
Okay. Are there any more questions? If not, let's try to click for the name for the lecture. Thank you very much. And tomorrow. Well, by the way, Clifford, could you send your note in PDF?
Yes,
format?
I'll send the notes to you probably right after this lecture. Yeah, or tonight, later tonight.
Yeah, and some reference to. Thank you very much. Bye bye.